Okay, cool. So starting with number one, we're solving for the driving force for the velocity profile in this pipe. And since the pipe is at an angle, there is gravity involved with it because it's not horizontal. So we have to account for both the pressure force and gravity. And that is being P1 minus P2 divided by L minus rho G sine theta. I did the exact same thing over here, just factored through my negative sign. And here the fluid is incompressible. It has to be viscous because it, it needs to have a viscosity to have a shear stress and in turn a velocity gradient, so it has to be viscous. I didn't say that over there. But it is Newtonian and it has to be isothermal because viscosity is a function of temperature. And since we're assuming that viscosity is constant, that means the temperature has to be constant. So it's isothermal. It's also fully developed and it's laminar. For here, we can say um, down here, we can look at the pressure force that we solve for up here. We can just plug into that and saying that it's 30 degrees. We can say that this whole term is greater than zero. And then we can isolate the P1 minus P2 term, and therefore saying that since that is greater than rho g L sine of 30 degrees, it's also greater than zero. In order to be greater than zero, then P1 has to be greater than P2. But for part D, when theta is 150 degrees, P1 minus P2 is less than LP, L rho G sine of 150. And since that term is also positive, we can't really tell with the information that we have if it's greater than, less than, equal to, or whatnot. So moving on to question two. We're looking at a vertical cylindrical pipe with water going straight down. I still have continuity the same on both sides, so there's no pressure gradient. In steady state, it's one dimensional, it's incompressible, Newtonian laminar. It has constant viscosity and density. So we can say that goes to zero because steady state, that goes to zero because it's one directional. This is irrotational, so it goes to zero, and you can factor out the density because of it being incompressible. So in both cases, we have du of z over dz equals zero. And for here, we use the z momentum balance, and I almost did the exact same thing on both sides. I wasn't paying attention when I did the first time around since the pipe is vertical and the fluid flows in the same direction as I defined my axes, then this rho g needs to be positive because gravity is going in the same direction as the fluid flow. So this is right. But for boundary conditions, it's the same thing. Little r equals zero, where dvz over dr equals zero, and little r equals big R, where vz equals zero. Then we can solve for the velocity profile by taking that velocity term that we took in the boundary conditions and integrating it twice. And solving for C1 and C2. C1 equals zero, and C2 equals rho g 4 mu times r squared. And plugging it all into the original velocity formula, we have rho g 4 mu equals big R squared minus little r squared. And for three, the finite differencing approximation, um, because it's a square channel, that means delta x and delta y equal one another. I didn't start out this around, oopsies. But if you take the mu equals d squared, bz equals dx squared plus d squared bz over dy squared and plus mu g equals zero, as your starting point, you can eventually solve down to 1/4 bz m plus 1n plus bz m minus 1n plus bz m n plus 1 plus bz m n minus 1 plus rho g delta squared mu, and this delta being equal to both delta x and delta y. And finally, for question four, we're solving for the velocity profile and for both, not the velocity profile, but it gives you the velocity profile. You're solving for the volumetric flow rate and the shear force from that velocity profile. So solve for the volumetric flow rate, that's W times the integration from 0 to h of the velocity profile that they gave you. And I split it up into two different parts to make the integration easier. I solved for the first part being the pressure driven first, and then I solved for the wall driven second, and then added that together multiplied by W to get Q. But that ends up getting you Q equals W times the entirety of delta PHQ divided by 12 mu L plus V velocity of the wall H divided by 2. And then you can solve the shear force acting on the bottom of the moving wall. So you're basically solving for tau to start with, and then you multiply that tau times the cross-sectional area, which is W times L. But to solve for tau, you have mu times v, the dvx dy over y equals 0. And then you can solve, that ends up being 2 delta ph divided by 2L minus velocity of the wall mu divided by h. And you can take that whole term and multiply it by WL to get the shear force. Woo, thank you.